Hi, everybody. It's Mr. Glenn Weiss here, your geometry teacher. Welcome to the first of our live sessions. No one is here with me today, and I so wish there were someone here to go through this for this presentation, but hopefully you'll be here. It's every Monday at 1 o'clock here in the conference tab. So we begin these with a little, kind of a little warm up here and maybe get a little bit getting to know each other. So this would be then, of course, shared in this would you rather question, but you can play along here. Would you rather have 10 siblings or no siblings? Here I might learn a little bit about your family. Number two, would you rather not be able to feel anything or be super sensitive to all touch? So we will go on from here. Oh, third one. Would you rather swim with sharks or swim with piranhas? I go with the piranhas. And I'm looking to do a wordplay because maybe I ran hastily. So I see that in piranhas. That's the kind of thinking you might do with math. And I'll show you. I didn't expect to come up with that, but I'll show you how to come up with thinking like that as we solve these, work with proof tables. It's a thing like that. If you were here, we do have our norms to be respectful, respect time, respect opinions, be mindful of boundaries, be courteous and curious, be nice, treat people with kindness, and then we do want to stay on topic. Hopefully it'll be interesting because I'm going to try to make it that way where you just see things a little bit differently. And here we are talking about proofs in Geometry A, Lesson 5. We have our learning intentions. I am learning about tools needed to do a proof. You've got the tools you need. I will demonstrate. Your success criteria, I can identify the necessary tools to do a proof and apply the tools to do an algebraic proof. There are many different types of proofs. Just a proof, tough one is a proof that, I don't know, God exists, right? The classic question. But we're going to not begin there. We're going to begin very basic with some numbers and adding and subtracting. It's too fast. Now, we do want vocabulary to help us organize our thoughts, to kind of link together what we're doing, package it up. That's what the vocabulary is for, help us give meaning. You've seen this already in the lesson. We have the hypothesis, the part of conditional, excuse the typo, conditional statement that follows from the word if, right? The hypothesis is in a sentence, other words, after if up until the comma. It's not conditional. We leave out the word if. So the conclusion is going to be the part of a conditional statement. Remember, they begin with the word if. So the part of a conditional statement that follows the word if. So it's all the words after the word then up to the period. You don't change any of these words. You just leave them as they are. That becomes your hypothesis and your conclusion, because we're going to start moving those and rewriting those into the proof tables. Now we have a conditional statement. That's where you see the word if and the word then. They always have those two words. If they have those two words, it's conditional. That means it's not always happening. It's something, it's a situation. Proof, that's an organized, logical way of presenting a list of facts that leads to a conclusion. So we'll have one sentence leading to another sentence to another sentence, like a daisy chain. Two-column proof, and that's just one of many different ways of writing a proof. You could do a paragraph, or you could take out the words and put them into their columns, and that's what a two-column proof is. So a proof given as specific statements in the reasons in a table format. So you have two columns, table. One will be this list of statements. The other will be the list of the reasons that those statements are true. Now, here are the rules we're going to use, and we'll see examples, but it's kind of good to at least hear it, right? So that when you see it, you kind of get that connection. You don't have to memorize these rules. you want to write them out so you get used to seeing it. So I'm just going to read through this list. Addition, property of equality. Subtraction, property of equality. Now, if you want, I'm going to interrupt myself. If you want to remember it, take a look at the pattern. The last words are always property of equality. So you have addition. You have subtraction, multiplication, and division. Those are the four operations of arithmetic. So you'll see what kind of giving you a heads up what to look for. If you have an equal sign, that means it's equality, right? Group down below, these are going to be statements more about the words, right? Above we have numbers. Below here we have ideas that will follow each other. Transitive, substitution, reflection, reflexive and symmetric. So we'll save seeing those until we get to examples, but you've heard it, you see it, so you kind of warms up your brain to it. Don't let the words scare you. This is the thinking we do every day. Very common thinking. It's just now giving us words for how we think. So we want to plan for a proof. So the first thing, now, we will give you in all of these lessons and workbooks and checkpoints and exams, we're going to give you a partially completed proof. So you'll already have the plan. You will be filling in the blanks. But you do have to know what you're looking at. So, how did the person who wrote that proof plan it? It didn't come out of nowhere. It was planned by somebody else, but you got to see that. So ask yourself, what is it that you are trying to prove? What the person who wrote the table or the proof table, what is it that that person is trying to prove? What steps did they take to get there? You need to get there. What reasons do you need? Okay, remember the reasons? On the right side, they support the statement. The statements, they tell it while the statement is true. And there are many ways to write a proof table. There's no skipping or skipping because the table is there for you. It's already a picture for you. So you want to be patient and go through every step, every row of the table. Hopefully in your mind you have a picture table with rows and columns. Tools, that's right. We have definitions, postulates, and theorems. And in fact, in geometry, these are the only types of answers that we have, except for a number. But a number has a reason being true by these because of a definition, a property, a postulate, or a theorem. So a kind of quick flash there. So let's get started here on the reasons, right? So here's the examples. So you kind of you've heard of these now, these properties of equality. So what I want you to look at, we'll take the first one, addition, property of equality. If A equals B, then A plus C equals B plus C. Now, what this tells us is when we add something, we have an equal sign, the left side equals the right side. That's all it's saying. Left side equals the right side. So look at the conclusion. It is the conclusion. The words after then that are important. Left side equals right side. And we add it. We have an equal sign. That's it. That picture. We give that picture a name. It can be any number. The only rule in there for the letters is that each letter gets a different number. You don't want to have this. So whatever A is on the left, it would be on the right. Whatever C on the left is the same number on the right. That's the important thing. A is not B, A is not C. They don't equal. Again, see the plus sign, we see the equal sign, we have the plus on both sides, boom. We call that sentence. If there were numbers in there, especially, because that's where it's more interesting, that's where you're going to map it back. So addition, property of equality. Now I'll go through quicker. Subtraction, you can see there's a minus sign and equal sign. Left side equals right side. It's equality. But multiplication, AC equals BC. The third one down. Below, division. See division sign, equal sign. We call that division, property of equality. The right side, now that's going to get a little more interesting. Here we have other properties of equality. And here we have, you got to think like there's things moving, things are changing, but there's still a truth when that change happens. So if the transitive property, what I want you to see here, there are three letters, A, B, and C. So there are three numbers or three sentences, like if a cow moves and the cloud releases rain, then when the cow moves, the cloud releases rain. But it could all that would be a true statement if if the condition was true. So it's three things: A, B, C. And then the daisy chain here is A to C. If A equals B, and that B, the same number equals C, then the A and the C, the beginning and the end must be equal. Those statements. So that's what we talk about, like things are moving here. The second one, substitution property. Here we're doing the movement is replacing. We put one number in for another. So if A equals B, then A can be substituted for B in any equation, equality. Example might be 1/2 and 1/4. No, I'm sorry, 1/2 and 2/4. Those are equal. So you can substitute one for the other. Now, a little bit of review, really quick. Transitive, you're moving A, B, C, three things. Substitution, two things. There's no C, there's just an A and a B. See how I break that down for you? If you know how to look for that, you can count 1, 2, 3, 1, 2. That really helps you know why something is true. Reflexive property of equality, A equals B. So this would be like a reflection. A could be you on the left side, but A on the right side could be a hologram of me. And that's all you knew. There's no other condition. There's nothing else. One looks like exactly like the other in 3D. A equals A. So that's a reflection exactly the same. So now we have only one thing. So we go 3, 2, 1, A, B, C, A, B, A, 1, 2, 3. The last one is symmetric property of equality. Now this is symmetry. This is like we had in symmetry if you fold a shape, an image in half, and it looks like the right side, excuse me, say you take a square and you fold it in half, the corners will match up perfectly. That's symmetry. But the positions changed, and that's what happened here. If A equals B, then B equals A. So the left side equals the right side, but the numbers are in different order. And when you get into the proof tables in our lessons, like the last step is going to be the silly lesson. I mean, the silly statement. You're going to like, well, what happened in the last step? I don't see anything happening. Well, yeah, because they had 2x plus y equals 4. And on the right side, it'll be 4 equals 2x plus y. And you go, well, it's the same thing. But that was, they put that in only for you to see that it's the symmetric property of equality. The left side equals the right side, but they switch the sides. This will all make more sense as you get into it. Now, we do have these postulates. So we've been talking about theorems, and then we have postulates. So remember I told you a theorem starts with, well, I didn't say this. Theorems are sentences that begin with the word if, the if then. If you have a reason that does not have the word if it's always true, it will be a postulate. So the first, we have the ruler postulate, like, you're probably, what is that? Well, use your imagination. Picture a ruler. You have a 1 inch on the ruler. Take another ruler, another 1 inch on that ruler. If you add up those two 1 inches, they will equal 2 inches. And very basic. We give a name to that, the ruler postulate. One inch plus 1 inch, doesn't matter where they come from. 1 inch of anything plus, well, it's got to be the same thing. 1 inch of a hot dog and another inch of a hot dog equals 2 inches of hot dog. That's the ruler postulate. So then you'll see more examples. That's kind of a fun one. Parallel postulate, arc addition postulate, right? So instead of inches, straight line, ruler, arc, degrees, we add those up, just 30 degrees plus 20 degrees equals 40 degrees. Angle addition, that's going to be like the ruler postulate, adding up the angles. Protractor postulate, that's where you measure. And the segment addition postulate. These are so closely related, it's hard to even find the difference. But that's what I'm here to show you, these differences. Okay, so we're going to need the vertical angles theorem. The vertical angle theorem states that when you have two lines that intersect, the opposite angles are congruent. All right, I'm giving you a little more information, but you can see that already. But we're naming these. So these are vertical angles. So 2 and 4 are vertical, 1 and 3 are vertical. So they're opposite each other. And I'm just going to throw a little more information. If you can picture scissors and you open and close your scissors, those opposite angles, like inside, like the bite, the cutting part of the scissor and the handle, right? As you open and close your handles with your fingers, the other part where the blades are, those will be the same angles. So we call that the vertical angles. Okay, before we get to a proof, I want to get into the lesson. So I'm going to do a little bit different here. And I want to kind of walk my talk sort of, and I want to take us through. This is going to be workbook 5.1. What happened here? 1 second. Here we have 5.1, 2-column proofs. So I want to show you what I've been talking about here in the lesson itself. And you've got these words kind of sizzling, bubbling around in your mind. I'm not sure really how this looks in the course. So you see in red proof, 2-column proof, postulates and theorems, right? And you see in quotes in bold, AB equals 7 units. So these are kind of the things that you're in. These are the tools. This is your tool kit, right? Here again, you've seen like in that presentation, addition property of equality. So this is also a good study skill that I'm demonstrating for you. As you read it once, you read it twice. You go to another source and you find the same thing in a different, slightly different context. It's green, it's blue, it's red, it's a different color. Somebody else is talking in a video. And your brain loves that because it's now, oh, I know this, and it's seeing it a little bit different, that tiny bit. So there's a little bit of video you could watch. I'm not going to kind of pass that through here, but we're going to go to this example. So we want to write a 2-column proof for this. So this looks like it's going to be there's a line, so segment addition postulate where we're adding up numbers. It says most 2-column proofs start with the information you are given. So here we see the first is the information is given. It's right up here. AC equals 7 units. That's the distance between point A and point C. And AD equals 13 units. So we want to prove that CD on the right, the small segment, is 6. Now we know that is true, but we're putting names, labels on top of the facts and what we're thinking. So here in this table below, they've repeated again step 2, same information as before, the given, and what we're proving is that CD equals 6. So here's the table. They went from the row 1, where it's given information. It's just copied straight down, but you will add in your assignments, in your workbooks and exams checkpoints, you'll choose the word given to go into number 1. And number 2, the left will be not to double use the word given, but you will be given the statement on the left side. It says AC plus CD equals AD. That's not told to us, is it? But let's look. AC plus CD. So they're not talking about B. They're talking about AC, that length, plus CD. That's going to be true because the parts always add up to the whole. Right? The sum of the parts, you probably heard that. Sum of the parts equal the whole. But we're going to call that, instead of that, which is also true, the ruler postulate. 1 inch plus 1 inch equals 2 inches. This is an example of that. But now we have line 3. It says 7 plus CD equals 13, because we know that AD, the whole thing, equals 13. So take a look, watch this for a moment. Did we subtract on the left side? We're reading from the top. Did we substitute anything? Do you see anything above that we substituted in? Substitution, subtraction, transitive, or reflexive. So you can rule out reflexive, right? There's no kind of mirror image happening here. Transitive needs 3 things in step 3, but there's only 2 things. So you can eliminate transitive. So now it's either substitution or subtraction. Did we subtract anything in line 3? No. But did we substitute? Look above. That's 7. Remember? In line 2, we see AC. In line 1, AC. And AC equals 7. And now in 3, we see 7. So there's substitution, property of equality. Remember, if it's not going to be one of the math operations, there's going to be movement. Either 3 things, 2 things, or 1 things are movement. And there's your reward. Good work. And there's another explanation. So you want to read that. Good study skill. You listen to it, you watch a video, and you read it. So there's another example, but I want to move on because you get the basic idea here. And I want to go on to 5.2 for you and talk about that. So this is just more examples. And there we were using the algebra, the numbers. Here we're going to use more words. So here we have a proof table, and I will walk us through this. Line 1 is, now this is just the table, right? We don't have a picture. We don't have anything given. And, well, in a separate place other than in the table. But the given is always the first row. So we don't need it like above. Number 2, the measure of angle A equals 90 degrees. That is always what you're looking to prove. So that's really like ding, 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 ding. That's really important. The first is the given. The second is the statement that's above the table where it says to prove. Okay, to prove. So we're giving us that angle A is a right angle, and you should picture it, right? It's a 90 degree. It's a hard corner. That's your 90 degree, like the four corners of a square. They're right angles, or four vertices, right angles. Right? And then line 2, that's going to be given to you also. Measure of angle A equals 90. So the reason here, you already know this. Most, it's reasonable, or you could look this up. Basically, it's like the definition. Number 2, the reason, if an angle is a right angle, then it has a measure of 90 degrees. So you can imagine where, like you're thinking a little substitution. Yeah, little substitution. You're thinking maybe it's a definition. Remember, that's one of the 4 things: definition, property, postulate, or theorem. But they're giving you this is talking about the plan. So you want to look at examples when you're completing your workbooks and checkpoints, because those examples will be the way the person started and planned that proof. So you want to do what that other person was thinking. You want to follow it. We're not going to be like creating or writing our own out of the blue, out of nowhere, proof tables and thinking. That's why copying is important in geometry. Side note, I do encourage it in our discussions, right? From a trusted source, type. A little segue here. Type, um, don't copy paste, and give your source for academic integrity. So here is another one. This is the linear pair postulate. Now I did tell you, I want to clarify something really important. I said if a sentence begins with the word if, it is a theorem. And if the sentence doesn't include the word if, then it would be a postulate. And here they have a postulate with the word if. That can mess you up on your exams and your workbooks and your checkpoints. For those out there, for that purpose, for your assignments, if there isn't the word if, it's a postulate. They're going a little loosey goosey, I guess, on this one. So you have to remember definitions. So supplementary angles are 2 angles anywhere on your screen or page that add up to 180 degrees. But here, the 2 angles are going to be part of a straight line, which is a 180 degree angle. So let's see how the person who planned this proof, what were they thinking? What were they thinking? So let's see. So we have the picture. We see 1 and 2. We are told up here that they form a linear pair. That means that they add up to 180 degrees. That's the definition. We want to prove that 1 and 2 are supplementary, that they add up to 180 degrees. So let's see. Given that, right, 1 and 2 form a linear pair, prove 1 and 2 are supplementary angles. So the first is always the given. Angle 1 and angle 2 form a linear pair. So next, since you know that 1 and 2 form a linear pair, you can use the definition of linear pair to write another statement. And then we got the given, number 2, blank statement, for which reason makes that blank statement true. If 2 angles are a linear pair, then they form a straight angle. That is the definition of a linear pair. What statement can be made using the given information in the definition of linear pair? The angle ABC is a straight angle. Angle ABD and DBC form a linear pair. Okay, linear pair, we see that in line 1, so that's a strong possibility. Then angle 1 and 2 are supplementary. Well, it says, remember I told you the last statement of a table is the prove line. Angle 1 and 2 are supplementary. So while the other statements are true, they are true, but you got to think the way the person who wrote this proof and this question thought. Prove 1 and angle 2 are supplementary. So that is what I'm going to click. So now it's telling me that I'm wrong, okay? It says, this is the statement you are trying to prove, but there are more steps to complete. So they are further breaking it down, okay? Which is cool. So let's go try again. So I jumped to, you hear that expression, jumping to the conclusion? That's just what was shown here, jumping to the conclusion. So up here, it says that we have supplementary angles. So that looks like angle 1 and 2 are supplementary. Up, it also says this is a statement you are trying to prove. A linear pair is a statement of adjacent angles whose non-common sides form a straight line. 1 and 2 form a linear pair, and their non-common sides is a straight angle. So that's a daisy chain of logic. So we're going to go here. Oh, so it is a straight angle. So we're jumping down here. So ABC is a straight angle. So it was that first one. Okay. And then the last one is what we're trying to prove. That ABC, that measure ABC is 180 degrees. So that is an example of how we think about completing our proof tables. So we are now at 32 minutes here in this session. I don't like to go much longer, but I do want to give you some other examples, a little bit more. But what you should do is to pause recording and go through this. It's in the workbook. That's part of completing the lesson for you. And it's always good to write your notes and then rewrite them again. So you kind of get that ownership for it. So here some more. I'm going to turn off my camera so we can focus on these examples a little more closely. So these are proofs involving segment or line congruence, lines being the same length. So for the first one, we have this line segment like a ruler, right? Because we're now kind of applying it to adding inches or units, PQRS. And we're given that PR, excuse me, that PR equals QS. And we want to prove that PQ is the same as RS. So the plan here is so we have, plan is When we subtract equal amounts from both, equal lengths from both, equal partials of both that are the same length, that, that we will be left after subtracting parts that equal the same, we'll be left with also parts that are equal to the same length. So think about this. If you have 8 inches and 8 inches and you subtract a 4-inch segment from both of these 8 inches, you'll end up with 2 4 inches that are equal because they're both 4 inches. That is what's happening here. Let's walk through it. So PR equals QS that we're given. Those are partials. Right? PR equals, they overlap. Right? PR and QS, they overlap. And then if we take PR, and that equals PQ plus QR, the sum of its parts, segment addition. Sum of its parts equal the whole. Next, QS equals QR plus RS. Sum of its parts equal the whole thing. 4. Q plus QR equals QR plus RS. Here, they use the lines 3 above to substitute, just like we did in that first example. Substitution. It's property of equality because we see the equal signs. They don't write that in there. And then line 5, PQ equals RS. So the parts that's left out, that's the addition and subtraction property. We added and subtract. Well, it's actually only the subtraction. I'm sorry. It's only the subtraction part, but it's addition and subtraction. So that is a quick walkthrough. Here, it's the same idea, but there's, instead of showing on one line segment, they're showing it on 2, but they're doing the same things. And if you just glance over here, you can see it's segment addition, substitution. We don't often see it given in the middle of the table, but it's how the person who wrote the question decided to do it. And then we see substitution in again. So it's the same logic of steps, but they have used, instead of one line, 2 lines. And here they cross the lines, but it's always the same logic. So I'll leave that here for you. Maybe pause to write it out as an example. So this has been pretty long and a lot of facts, a lot of information. Here, this would be, if we were in the live session, this would be the exit ticket here. And just to review the questions, in this lesson, I give you 4 types of reasons or tools, thinking tools, that you will use in a proof. What are those types? Definitions, properties, postulates, and theorems. Last question. What do you think will be the hardest part of doing proofs? So there's no right or wrong, but just to reflect on what we've done, to think about what will be challenging or not. But that is what I have for you. I'm going to quickly just turn the camera back on. And so I hope that you enjoyed and found this interesting. These are puzzles. For those of you that like puzzles, this should really be very interesting. But those who don't like puzzles, be patient. It's in you. You've got it. You can do this. It does take copying the examples and getting to a comfort level with it, but you always don't memorize things. Have examples and pull and just move it over, move the information over from a similar example of a proof to the one that you have in front of you. So take good care, and as I end each of my recordings, take good care of yourself and take good care of someone else too. Bye for now.